Hi everyone, my name is Jay and today I'll be presenting my final year project Skin Cancer Detection with Deep Learning. For some motivation, skin cancer is very common. It is one of the most common forms of cancer in the United States and more than 1 in 5 Americans will eventually suffer from it, which is a very troubling trend. Early detection of skin cancer is the key and detection can be easy as compared to other forms of cancer. This is where deep learning models come into play where they can be used to detect whether a lesion is benign or malignant. Further, they even determine that what kind of lesion it is for further diagnosis. In this work, we introduce four main objectives. Firstly, we introduce a deep learning model that detects skin cancer and that can determine whether a lesion is harmful or harmless. Secondly, we do extensive result validation. We do it by having a fixed test set on the HAM 1000 dataset, as well as we do extensive benchmarking based on the current literature and work which is available open source. Thirdly, we develop a mobile application in which we deploy the model and we demonstrate the usability of the model in a practical use case. And finally, we do discussion and review on many topics related to the data that we used, the deployment strategies that one can have, the current benchmarking schemes which are available, as well as ways in which we can reduce the weight of the model for easier deployment, that is pruning. To train the models, we use the HAM 10,000 dataset. It consists of 10,000 dermoscopic images in 7 categories. Before training, we do some data pre-processing that includes image normalization, some rotation, flips, zooms, and other things. Also, after the model training is done, we measure the performance of the models using various metrics. Some of them include precision, recall, macro average F1 score, and other precision recall curves. Now, for training the models, keratosis, carcinoma, and melanomas is labeled as harmful, whereas the remaining categories are labeled as harmless. In this, 10% of the dataset is randomly selected for testing, whereas the remaining is split into training and validation. 7 base CNN models are chosen for training on the dataset, and the models are shown in the slide below. Based on the results, 4 top models are selected on F1 score and the area under the precision recall curve. And finally, an ensemble is created by averaging their outputs. Finally, the performance metrics of the ensemble deep learning model are reported. After all the training results, the 4 top models chosen are DenseNet 201, Inception ResNet V2, EfficientNet B4, and B6. In this case, we obtain a F1 score of 0.91, an accuracy of 0.94, and area under the precision recall curve of 0.93. In general, a performance boost is seen across all the chosen metrics used for analysis, such as precision, recall, and F1 scores. The precision recall curve is depicted on the right. Now let us talk about the mobile development. So we have developed a backend which is deployed on DigitalOcean. We have developed a front-end application using React Native which is deployed via Expo. Here is the demo of the mobile app. So firstly, we open the camera and scan the QR code and the application opens in the Expo app. Afterwards, we can sign in or log in into an account. So I do that with my own account here. Afterwards, I will select the scan feature. I can either use my camera roll or upload a photograph. So here I will use my camera roll and select one of the lesions photo. Once I do that, I will be prompted with a weighted Glasgow checklist with which I can determine whether the lesion is suspicious or not. Once all the questions are answered, the image is fed into the machine learning model and I can view the results. So here the model says that there is a 50% chance that the lesion is harmful based on risk assessment as well as the photograph. I can choose to learn more about the lesions and I can also choose to save the photo and view nearby hospitals. So this is a quick demo of the app itself. Now for some discussion and review. In this project we have used the HAM 10,000 dataset However, there are many other datasets available with which we can combine together and create a master set so that we have more data for training. Also, we see that there is a test set mismatch because the images used for testing are professional dermoscopic images which are aligned properly and very clear. However, the images taken by camera might not be of appropriate quality. Also, there is some sort of selection bias in the dataset. It is so because there is underrepresentation of darker skin types. It is important that all the images are representative for all populations such that we can reduce algorithmic biases. Next, about benchmarks. We see that there is a lack of standardization when it comes to benchmarks. It is so because all the studies use their own performance metrics, and some of them employ dermatologists to measure the performance of their model rather than a fixed test set. It is to reduce the Bayesian error because we know that even dermatologists don't have 100% accuracy when it comes to detecting lesions. After the deep learning model is exported, it is quite large, close to 500 MB, which can be troublesome in deployment in resource constrained environments. Also, it leads to longer inference times. So, another area worthy of exploration is compressing and pruning the model to reduce its size. And finally, let us talk about multi-class classification. So there can be two variants of the ML model, one for at-home unsupervised binary assessment, which works in conjunction with a smartphone application, as well as at a clinic supervised assessment, which can take high-resolution photographs and can also classify the disease into more fine-grained categories. Thank you. And a copy of this FIP report is available to download at the digital repository of NTU.